I'm going to I'll give an overview of life course methodology. I'm not going to quite cover, I don't think, all the topics that are listed in the title on the agenda. I'm going to focus mainly on the statistical methods, but we'll touch on some of the other aspects of methodology as I go through. So, of course, with life course epidemiology, we need longitudinal studies. We have a long time lapse between the exposure that we're often interested in and the outcomes that we measure. We need to consider the temporal dimensions of the variables. We have this long time period means that we have to consider a whole range of confounders, mediators, and effect modifiers between those 2 points. And we often have repeated outcomes and/or repeated exposures. So how do we test life course models? Well, as I said, we require an understanding of the ordering of the variables across the life and their interrelationships. And it's difficult, if not impossible, to test our whole theoretical model in practice, because we might not have all the data that covers the whole model, or it might be too complex. And so what we try and do is to break it down into simpler testable parts. Now, an initial focus in life course epidemiology methodology has been on modelling the effect of a repeated exposure measure, and most often growth and social composition, and that's what I'm going to speak about today, on a later health outcome. So this is where I really came in, because I was employed by Di and Mike as the statistician on the study over 20 years ago now, and I was asked to look at how you could relate repeated measures of body size with blood pressure later in life. And this is really what got me interested and is what kept me on the study for so long. This was sort of where I started. So the problem is with a repeated exposure measure is you've got this problem which we call the duality of size and growth. So if you know size at a time point t and a size at time point t plus 1 sometime later, you also know the change. So it's a bit like an age period cohort effect. Similarly, if you know the size at t and you know the change, you then know size at time t plus 1. So this means that there are multiple ways to parameterize the same model. So these models have the same model fit, but if you're not careful in the way that you interpret them, you can come to very different conclusions. And I think at the start of life course epidemiology, people were fitting these different models and not really understanding the implications. So these are the equations of a model, size at t and size at t plus 1, and the size at t plus the change. And you can see there that the coefficient for that second term in both of those has the same coefficient. So we can interpret that in the same way, but you can see the coefficients for x plus x1, that first time point, are very different. So if you try to interpret that, you can come to very different conclusions. And that equation can extend to more than 2 measurements, which we've shown in a paper in the AJE in 2006. So both these types of parameterizations have been used, so you don't need to know the details or see the details of these, but the first one is this one where we've just put in the size at each time point, so multiple size measures in the same equation, and then the estimates are plotted. And then the second sort, which Di showed examples of in the previous lecture, where we start off here with a baseline at 2 years, and then we put in the changes. So both types of models have been used. So that first example is what Tim Cole has called a life course plot. So this is the one where you're adding each size at each age. But of course, you've got highly correlated values, particularly if you've got repeated measures at very short time intervals. So you can see here on the plot that you've got wide confidence intervals, and actually some ages don't improve the model fit. So what Tim Cole suggested you can then do is to remove those uninformative ages. And so then on this life course plot, it kind of gives you a visual representation of the size and the change. So you join these up and that gives you the change. So here you can see that there was low body size related to blood pressure in the early years, and then we have this rapid change so that it becomes that high body size, high BMI in later ages is associated with higher blood pressure. So the interpretation depends on the conditioning. These are different conditions on the model, and I think this is quite a nice diagrammatic representation that was in the IJE in 2014 by a previous colleague of ours, Andrew Wills. And I think I've got to do that. Yes. So the first red line represents that size model. So this is the life course plot. And this is saying that given the same size at all other time points, you have a bigger size at a single time point. But then you go back and you have the same size at the other time points. Whereas that model where you put the change scores in is represented by this line, which says that you have the same change in all places, apart from this change between 2 and 8 years. And so you can see that the conditioning is very different there to the life course model, even though it's actually the same model fitted. Another approach that's used, and this was the one that was used a lot by David Barker, as his statistician Clive Osmond has proposed this and used this a lot. And here we remove the influence of earlier exposure. So this is a conditional change model, where you do a regression model of the exposure at time t on the prior measure or measures, and you do this by sex, and you extract the standardized residuals. And this gives you the change above or below that expected in your given cohort, given previous exposures. And this is useful in capturing accelerated or restricted growth in particular. And this is an example where we've used it looking at BMI change and blood pressure at 53. And what this does is it gives you a series of uncorrelated variables. So now when we put those change variables, those 3 change variables in the model, they're uncorrelated, so there's no change in the estimates. But what it does allow us to do then is to test whether there's a particular period of growth that's more or less important than the other periods. So the interpretation of this, again, it depends on the condition. Again, this can be shown to be exactly the same model, but here you're only conditioning on prior measures. You're not conditioning on what goes later. So it had been suggested that path analysis might be a better approach, where you could estimate the indirect and the direct and total effects. And here, this is just an example. So you've got the combination of the size and the conditional models. But if you just do a straightforward path analysis, then you'll get the same results as you do from a traditional regression analysis. Path analysis might come into its own when you're adding additional variables. Now, for the NSHD, these types of approaches can easily be used because every participant is measured at exactly the same age, although you do need every participant to have every measurement at those ages. Of course, we can employ missing data methods. For example, we've used multiple imputation to allow for this missing data. And people do get rather worried about this sort of collinearity of the measures, but I think when you read Tim Cole's paper, when you go back to his work, he says we'll remove redundant measures, and this can either be done from a statistical point of view, or we often predefine the biological periods of growth that we want to study. So although it can be a problem, if you think about the periods of growth that you're interested in, it's less of a problem. So I've called these two-stage analyses. So there was a lot of work, a lot of ideas of how we could better model growth in relation to a later health outcome. Most of these involve fitting some sort of random effects model to the repeated measures of body size, extracting characteristics from those individual fitted curves and relating those individual characteristics to a later health outcome. Now, I've called these two-stage analyses because generally it's done in two stages. There's a multi-level model with the extraction of those coefficients or those for each individual, and then a second model relates them to the health outcome. However, as you can see in the example here, there are multivariate models where you can actually do these two things together, which are becoming more popular. So various things that you can do to fit your models to the growth measures, polynomial models, spline models, sitar, and I'm going to give examples of those in a minute. But the thing about these models is that they deal with unbalanced data and they deal with missing data far better. Although in the NSHD, we don't have so much to gain from these models because we do have these repeated measures at the same age in everybody. So the top example is fitted to data in the NSHD. And here it's fitted to BMI, and we extract the characteristics of the BMI trajectory. So for example, that area under the curve, that can kind of be a BMI accumulation of BMI years. We can look at maximum BMI, age at maximum age, adiposity rebound, and then the second graph over to the far side is looking at acceleration, so you can look at things like peak velocity. But of course, there's a huge number of aspects of that curve that you could extract. So one question is, well, what do we extract from data like that? Another approach that's gained a lot of popularity, which was developed by Kate Tilling and colleagues at the University of Bristol, is to use linear spline models. So here you extract the linear rate of change over different periods. And again, this rather comes back to what periods of growth or development do you want to consider? Where do you put the knots between those linear splines? This has gained a lot of popularity and been used a lot. Another approach, and I'll show an example in a later session, is this sitar method that was developed by Tim Cole. And here he summarizes everybody's growth curve through adolescence using 3 parameters for each individual. And you can do this for height or weight. I kind of really need to point, so I hope we can see this. So the first parameter is size. So you can see the black line in the middle, that's kind of the average. And then the size parameter shifts each individual's curve up and down. So they're the red curves. It just shifts up or down. And then we have the tempo, which is basically the relative timing of puberty, and it's based on age at peak velocity. And that's the blue curves. So you're shifting along being a late developer or an early developer. So you've got the up and down, and you've got the side to side. And then the third parameter is velocity, which says how quickly you go through puberty. And that's the rotation. So that's the green line, so that's rotating that curve. And he shows very nicely that generally you can explain a huge amount on nearly all the variation in individual growth curves by these 3 parameters. So you extract these 3 parameters, and then you can relate those to an outcome. Another approach to summarizing the trajectories is to extract latent classes, so either using latent class growth analysis or growth mixture models. So Di showed this example, which are overweight latent profiles that were extracted by Richard Silverwood. Now, of course, these classes tend to be data-driven, and they contrast the whole trajectory. So you can't pick out specific aspects of the trajectory because you've got to compare whole trajectories. And often it depends on how the data-driven classes come out. This was quite nice because, as you can see, you have this pubertal onset overweight as well as a pre-pubertal only overweight group. So you have these crossover groups, whereas sometimes you'll find, or quite often you'll find, that you extract classes and they're just medium, high and low groups, which aren't so useful. So now I'm going to talk about some work we've done looking at the accumulation of socioeconomic position across the life course, though it can be applied to other exposures as well. So just going back to the critical period and accumulation models, Di showed the critical period model, which is the one at the top. So it's exposure at a single time point, has an effect on the outcome. And then we have the accumulation model, which initially was defined using different exposures. But what we've done in this case is that we look at accumulation of the same risk factor. So this is accumulation of SEP across there, which can also be seen as a sensitive period model, can be sort of seen on top of that as a type of accumulation model, because here you've got one time point having a stronger association. So there is this link that the sensitive period model and the critical period model actually can be seen as sort of nested within the accumulation model. So where this came from was that people were testing this accumulation of disadvantage across the life course. But what we showed was that if you test accumulation, you say that accumulation fits the data. Whereas actually with the same model or the same data, it might actually be that it's only one time point that's actually driving that association. So your a priori hypothesis really affects your conclusions. So what we wanted to do was to look at alternative competing models. How do we select the most appropriate life course model? So I'm going to use the example that we used in our original paper, which was first authored by Geeta Mishra. And this was an example with socioeconomic position at 3 selected ages, representing childhood, early adulthood, and midlife in the NSHD. And to make this work, we had to categorize into manual and non-manual classes, so we had to have binary outcomes. And this is kind of the hypothesized DAG, which is very simple, and it does ignore any confounding on any of those variables. So, as I say, we had these 3 variables at these 3 selected ages. Then we parameterise the model, first of all, as all possible socioeconomic pathways or trajectories, and that's the saturated model. Then we define an accumulation model, and we do this by just adding up the scores. So each of the 3 time points, we score 0 for the most advantaged and 1 for the disadvantaged. So we have a score between 0 to 3. Then we have 3 sensitive or critical period models, childhood, early adulthood, and midlife. And then we did also define social mobility. And it's dependent on how you define social mobility as whether you can actually disentangle that from an accumulation model. So we define social mobility in these cases as being an interaction between an earlier and a later life variable. So each of these models is nested within the saturated model, and you can use an F-test to compare those. And it's actually non-significant tests, so non-significant ones that we want that suggest that that restricted model fits as well as the saturated model. So just so you can see what I mean by the saturated model, this is where each of the 8 possible trajectories, where M is manual and N is non-manual, so there's 8 possibilities, they all have a different mean level. And that's the model with all the main effects, plus the 2-way interactions and the 3-way interaction. And I just wanted to, I put this up so I can highlight first the SEP score. You can see that I've ordered it from those that are always non-manual to those that are always manual at the bottom. And you can see that some trajectories are far more common than others. So this does limit the power in disentangling these hypotheses. So this is the example with life course SEP and BMI in NSHD. So that's just the table of the F-tests, and you can see that we select as the best fitting model accumulation for women and the early life critical period for men. And then you can fit the model and produce the estimates. Now this is where we found that if only testing the accumulation analysis, or if only testing the accumulation model, the analysis would support a hypothesis in the men, because you can see that the accumulation is significant, but it's driven by that early life factor. Now, this approach has been used by us in other examples and by other research groups. And for example, this paper looked at an additional model. Additional models have been added. They called this the relaxed accumulation model, which instead of adding up the components allowed each of the three variables to have different coefficients. But it's become clear that choosing the best fitting model is actually rather challenging. You can get cases, as you can see here, that more than one model fits as well as the saturated model. Which one do you then choose? We've toyed with using either the highest p-value or things like the BIC. And it's p-value driven, so results are dependent on the sample size. So if you have a very large cohort, then all your models give significant p-values. And if you have a smaller cohort, then all of them are consistent, all the models are consistent with the saturated model. So Andrew Smith and Kate Tilling at Bristol started to develop an alternative approach to model selection. And I won't go through the details of that, but there's now 2 papers. And one of the nice things about this approach is that it can be extended to continuous exposures, because our approach was for binary variables, whereas this can be extended to continuous exposures. And in the recent edition of the IJE that Di showed, we have a paper on that. So here, it's a similar approach in that you encode each potential hypothesis as a variable or variables, and you want to identify those with the strongest association with the outcome, with the fewest parameters. Now, because there are more variables than degrees of freedom potentially, you have to use a selection procedure based on the least absolute shrinkage and selection operator, and they've used least angle regression to do this. So what you get here is that you plot the R-squared against the number of variables as they're selected in at each stage of this procedure. And what you're looking for is to choose the elbow. So you choose the variable where you see an elbow. So you can see for men, and this again was, they used the example of the NSHD, which I've just shown, and you can see there's an elbow at 1 parameter for the men, and probably, it's not so clear for the women, but probably at 3 for the women. And these did select the same models as in our original example. So the men, that was for the variable that encoded the early life critical period, and for women, it encoded the accumulation. What they showed in the first paper was that the LARS outperformed the F-test approach in simulation studies. And just going back to the causal model, we think that this is a good way to investigate which model fits the data best, but then subsequently you might want to apply more complex models, allowing for confounding and mediation. And this is also a paper that we've been involved in with the Bristol group in the current IJE, where we've shown that there is a relationship between mediation analysis and this structured life course approach, so they can be considered to be linked, and you can show that each life course hypothesis suggests the presence of a specific set of mediation or interaction terms. Of course, conventional regression-based mediation analysis, which this is based on, has well-documented limitations, collider bias, intermediate confounding, and so we're more and more thinking about using the more advanced mediation methods, which are based on causal inference. So I just wanted to say, so the challenge with life course epidemiology has been more about the dealing with repeated exposure variables. But I did just want to say a little bit about repeated outcome variables, although methods are very developed for that. But I think, and we showed in the 2014 book on healthy aging, a chapter that I wrote with Debbie Lawler, that actually surprisingly few studies always utilize their repeated measures of an outcome appropriately. And still, it's not always modeled appropriately when they do. And I think we could do a lot more to actually model the data, the repeated data that we do have to look at the risk factors for age-related change. So Di mentioned this about how we've used multiple cohorts. So for something like blood pressure, we still don't have a study because we want to look at within-person change, but we still don't have a study that has blood pressure measured in the same individuals right across the life course. So what we did here, instead of using cross-sectional data, we used multiple longitudinal studies to piece together the whole life course trajectory for blood pressure. So we had studies that covered different but overlapping periods of the life course. Although because of potential cohort differences, we focused particularly on the rates of change. So that's the acceleration, which you can see down here at the bottom, and identified 4 different periods of change. And I'll talk more about this in the cardiovascular session. I did just want to mention that when you've got a long-running study, in the NSHD and some of these other studies, the machine used to measure blood pressure changed. So we had an old random zero SFIG in the early years. We changed to an automated device. And actually we showed in this that if you didn't correct for that change, you overestimated the rate of change in blood pressure in midlife. And of course, it has implications also for comparison across studies if they're using different measures. And we're looking at cohort differences. So we've just carried out what we were going to call a calibration study, but it's now an equipment comparison study with 118 individuals that weren't part of NSHD. And we've done a randomized repeated measures crossover trial to compare our two measures, 2 machines for blood pressure, 4 machines to measure grip strength, and 2 machines to measure lung function. So I just wanted to highlight these methodological challenges when we're looking at trajectories across the life course, even when we think, or even when we're measuring the same thing. Now, purposely in that first paper, we didn't combine the trajectories because of these challenges of different measurements and different cohort effects. But we did work with some statisticians who kind of produced this. We produced a sort of proof of concept paper showing how a Bayesian approach could be used to kind of knit together all those longitudinal trajectories. Now, this is the plot that came out of it, and this is what is possible. You can do it, but we still haven't added in the sort of cohort effects and the risk factors into that. So more work needs to be done to be able to apply these models, because obviously it'd be nice to apply a model that went across the whole of the life course looking at risk factors. And I think more and more what we're actually looking at is 2 processes, 2 functional measures changing together. So I think this is what we're going to need to develop in future. This is just some examples, but here we've still got a time-varying covariate with an outcome, but often you don't know which is your outcome. They're just 2 processes or more going along together. And at the moment, this can often be influenced by the data availability. So does one factor predict another? It kind of depends when you've got each of those measured in your cohort, where actually what's happening is these things are tracking and changing together. And finally, I just wanted to say a little bit about how we can use cohort studies to go beyond associations and to try to get at causality. So of course we can use the statistical methods, and I've used an example of instrumental variables. They're very popular at the moment, Mendelian randomization, which can be used to look at causal associations, but also thinking about study designs and the use of cohorts. I think we need to look at more ways to not just meta-analyze data, but to synthesize data from different evidence. And then also thinking about how we can use family-based studies and cohort comparisons to get at causality. So I've just finished by showing a couple of examples which I think are really nice to illustrate this idea. So this is a cross-cohort comparison from the ALSPAC study and the Pelotas cohort in Brazil. I don't know whether you can see it, and it would be nice if I could point it out, but the top plot shows the association between breastfeeding and systolic blood pressure, diastolic blood pressure, BMI, and IQ in first ALSPAC and then the Pilates cohort. So what you can see is that breastfeeding, that line, those two lines at the bottom, breastfeeding in both cohorts is associated with higher IQ in the children. Whereas for systolic blood pressure, diastolic blood pressure, and BMI, breastfeeding in ALSPAC is associated with lower levels of those risk factors, but it's not associated with those risk factors, or it might go the other way in Pilates. Now in ALSPAC, which is in the Avon area of England, you've got a lot of confounding of the women who breastfeed in terms of their lifestyle and their socioeconomic advantage. So more advantaged women are likely to breastfeed. And so even if you adjust for all those confounders, you still might have residual confounding. Whereas in Pilates, you don't have that same confounding structure. So then testing that further, because obviously the Pilates cohort is quite small, there's quite wide confidence intervals. Testing that further, doing a comparison between ALSPAC and a meta-analysis from the Cohorts Consortium, which includes Pilates, but is based on 5 cohorts from low and middle income countries. So you can see that you've got those more precise estimates, and you can see that if anything, they're going the other way from those in ALSPAC. So the conclusion from this might be that although breastfeeding might have a more likely to have a causal effect on cognition, it's not likely to have a causal effect on blood pressure and BMI. And then thinking about how we can use parental, both maternal and paternal behaviours to try to separate out environment from intrauterine effects. So an example of parental smoking during pregnancy and offspring health. Here, comparing the associations between smoking in pregnancy in the mothers and smoking in the fathers and the offspring health. So in one example, we see maternal association being stronger than paternal association for childhood conduct problems, and again, this is in ALSPAC, suggesting that's more likely to be an intrauterine effect. Whereas for bone mass, and this was actually in girls only, the maternal and paternal associations had similar sized associations, so suggesting that's more a shared environmental effect. And I'll show another example of something we've done looking at both male and female comparisons to try to get at the mechanisms. So just some final thoughts. I think I'm often asked, what's the method for life course? What method should I use? But really you need to match the method to the research hypothesis. You need careful interpretation and you need to understand the assumptions. And this is where I think causal diagrams have been helpful, because it has allowed us to think about understanding what the assumptions that we're making. The aspects of your particular study will influence the choice of models, particularly as, say, whether they're balanced or unbalanced, the repeated measures, because you don't have the option of all of the approaches if you don't have balanced data. I think sensitivity analyses are useful. I think it's always worth thinking about how study design and analyses can help with causality, and something that I haven't mentioned, but that does need to be considered in all epidemiology, as well as life course epidemiology, is the impact of missing data and measurement error and those sort of things as well. Okay, thank you.
So my question for you, Rebecca, is of all of the approaches that you've looked at, I know you have to make some decisions based on the type of data and structure of data. Do you think this is still evolving in terms of best methods?
Yes, definitely. So I think these sort of causal inference models, as I say, I think they getting us to think more about the assumptions, and I think that was the challenge initially, that methods were being interpreted without understanding the conditioning and without understanding the assumptions. So it's really understanding those.
Right. And I know we'll get to this later, but how that translates to policy decisions as well. And when do you say you have enough data to say this should influence policy?
Yeah, I'm always wary on saying that on a single finding on a cohort study. So systematic reviews, meta-analyses are really useful. But this idea of pooling evidence from different domains and different areas of research, I think, is one that we should look at.
As a recent graduate from a doctoral program in epidemiology, I know that, and I shouldn't speak for all US programs, but I think we are getting more advanced in teaching of causal inference, but I certainly don't think that the causal inference is being applied at least uniformly to life course methodology. And so I wondered from your interactions, particularly with other colleagues around the world, if this is becoming taught more widespread, or how students who are interested in this could get more information on these types of methods.
I mean, I think it is being taught more. I think the trouble is it's challenging. And so when you're thinking about all the possible, and we'll talk about this tomorrow, you know, your causal diagrams would just be so complex. So, and I do like the quote of George Box about all models being wrong, but it's just how wrong they have to be, or how right to be useful. So I think it's helping really with understanding the assumptions. But you know, even if you use a causal or some more advanced analyses, then you've still got assumptions on that. There's still something you've got to make assumptions about.
Hi, thank you so much for your presentation. I have a question around and wanting your thoughts around qualitative research and how, if you think there is a place for qualitative research in any of the approaches you discussed, and if you've used qualitative research in any of the studies, the life course approaches in terms of including it within some of the data that you're capturing.
So what do you mean by qualitative research?
Qualitative?
Oh, qualitative research. I think there's certainly a place for qualitative research, and in our Healthy Aging book we had a chapter on qualitative methods. Di's actually done more work on the qualitative methods, but I think having those two together, there's certainly a place for it, yeah.
Hello, thank you so much for your presentation. I was really fascinated by the slide toward the end talking about separating like intrauterine exposure versus from the environment. And for me, that just seems so challenging just because of the intricate connection of the mother's body and how it is affected by the environment. And you talked a little bit about smoking and looking at maternal smoking versus like paternal smoking. Are there other methodologies that you've used to kind of look at this effect separately?
I mean, they weren't our studies looking at the parental smoking, because in NSHD we didn't ask for parental smoking.
Oh, right, the paternal versus maternal, right? Yeah.
So these are they're just sort of a way of, it's not the answer, but they're ways of getting at whether it's more likely to be something. And of course, the environment might also impact through the mother onto the fetus. But it's just a way of getting at whether it's more of a biological effect or more of a shared family environment. And I do have an example this afternoon where we've looked at the effect of whether the effect of pregnancy is biological or more about family lifestyles. Mm-hmm. Again, comparing men and women about their. So it's sort of not the answer, but it's adding to that evidence that perhaps it's more one than the other.
Yeah, I just want to add to the discussion on this. In the Danish cohort, we also employed this paternal-maternal comparison, but also being commonly used as sibling control design. For example, if the mom smoked in one pregnancy and did not in the second pregnancy, or vice versa, then you compare whether smoking causing the interior effect or whether it's from the environment or family factors that do not change over time. But all this method has some assumption and limitation. For the sibling design, you often don't get enough of this discordant exposure contrast. So there are other issues, but there are some methods being discussed and developed.
Exactly,
Yeah.
so that's an example. I mean, there's lots of examples where you can twins and siblings and the maternal, paternal.
And then you need the 400,000 person cohort study. Any other comments, questions? Oh.
This came up a little bit earlier, I think, in Diane's talk, but for both of you, what's the thinking on possible iatrogenic effects in cohort studies? Is that a possibility, or is that ever considered a possibility? That how that might change, outcomes to some degree.
That they're in the cohort.
Yeah.
So yes, as the examples showed, and we know that people that are staying cohorts are healthier than the general population. So I don't know whether there's anything we can do about it. I know from an SHD that we still have enough variation to look at association, so it's not like it changes everybody's life course. But yes, it does change. But I don't know of a way of sort of being able to correct for that.